Dear friends, colleagues, students, members of the public, and members of the Australian Institute of Building. Good evening and welcome to the 2014 Australian Institute of Building Annual Address, How Do Buildings Burn? That will be presented by Professor José Torero, Head of the School of Civil Engineering at the University of Queensland. My name is Paolo Tombesi. I am the Chair in Construction here at the University of Melbourne, and I will be your host for tonight. And on behalf of the University, the Faculty of Architecture, Building and Planning, and the construction program within it, I would like, first and foremost, to take this opportunity to thank the Australian Institute of Building and the President of its Victorian Chapter, David Burnell, for being the critical catalyst for this event, and the Hansen Juncken Construction Company, a long-standing supporter of our faculty and program, and thank them for sponsoring it. Now, we see today's event as a beacon, and not only because the discussion will be about fire, but mostly because we would like this lecture to reaffirm the course of our program and the way in which we publicly engage with the discipline on one side and with industry on the other. As you may know, the symbol of our university is Nike, the goddess of victory and the brand behind the Just Do It slogan. Yet the symbol of civilization is another one, Athena, Minerva for the Romans, the patron of the quintessential city and the goddess of knowledge, wisdom, justice, the arts and war. And Athena is often depicted carrying an owl on her arm, the bird that sees well into the night and is upheld as a symbol of perspicacity and erudition. Now, according to the myth, Minerva keeps the company of the owl so as to benefit from her companion's unerring sight into dark or distant territories. And we at the university want to believe that in today's world, we are the precious owls of Minerva, particularly within those professional disciplines that have a concrete mandate in the present, and construction, of course, is one of them, which can only push the speculation so far in practice. And indeed, it is the predisposition to be intellectual visionaries and steerers, if you will, which makes us worthy complements to Minerva's mature wisdom. Hence the owl behind me. We would like to make events such as this an opportunity for the dissemination of foresight and the critical analysis of current jurisdictions, with the intent of facilitating reflection and eventually promoting discussion outside these walls. And so our exceptionally distinguished owl for tonight is José Torero, who will try and make us understand the dynamics of the encounter of natural elements with man-made structures and spaces. Before I introduce our speaker and try to introduce the topic of tonight's address, let us acknowledge the traditional owners of this land, the Wurundjeri people of the Kulin Nation, and pay respect to their elders, past and present. And taking lessons from the past is a necessary condition for any institution that aims to move forward in any meaningful way. In the case of tonight's event, is even more so, given the importance that fire management has had in the long history of the human inhabitation of this continent. Now, the social and cultural effects of fire on people's lives and behaviour are equally profound in modern and contemporary history. Take this existing building in New York, currently on the grounds of New York University, originally the site of the Triangle Shirtwaist Factory, which provided the spark, and the pun unfortunately is not intended, for the establishment of the International Women's Day on the 8th of March every year, to mark the loss of the 123 women and 23 men trapped in the factory when it was gutted by fire in March 1911. Sadly, the history of New York in the world's collective imagination has become one inextricably linked with fire due to criminal events that I don't need to recall here. But in fact, a litany of dramatic encounters between built environment and natural elements marks the entire geography of our settlements. Now, if this is the case, how does academia and our built environment courses deal with fire and other types of hazards, either natural or man-induced? So let me get personal for a moment at this point. This is a photograph of a fire brigade battalion in Europe, roughly 30 years ago. And I know this photograph well because I was in the picture as an architectural engineering student. At this time, the university courses in my country and in much of Europe at that time, Italy, and much of Europe, France and Spain and other places, had no generic curriculum remotely touching the topic. Students were taught how to design, how to engineer, how to construct buildings, sometimes by trying to respond to code. But fire was never consciously part of the cultural cone of vision. And 30 years later, considering that buildings had become much more complex, the situation is not significantly different. We have renowned research centres and a few programs that are devoted to it all around the world. Yet outside of these precious instances, which are the domain of specialists and the territory of applied science, the predominant educational culture in building, but in architecture and construction, does not look at safety in these matters as a creative design factor, but rather as a risk to neutralise through normative checks. Planning in Victoria and Australia in recent times has been providing a welcome exception. But by and large, the technical and cultural aspects of fire management in building are, in a sense, still separate. And this is why the opportunity we have been given tonight of listening to the words of José Torero is precious. He graduated in mechanical engineering from the Pontificia Universidad Católica del Perú in Lima, the same year the young firemen graduated in his course. That's why I had that photograph, in order to show you the amount of time that passed ever since. So Professor Torero moved after his degree to the University of California at Berkeley to earn a PhD on smouldering combustion and fire safety. And for the last 25 years, he's been at the forefront of fire safety studies as a scholar, as an experimental scientist, a forensic analyst, and communication giant, and a champion of disciplinary inclusiveness. Going through his curriculum vitae makes you dizzy for the breadth of his interest, service and recognitions, the depth of his contributions, and the geography of his movements. He must have decided to wage war on built environment hazards by using Athena's weapons and Nike's winged shoes. After California, he moved to the University of Maryland and eventually to the University of Edinburgh in 2001, where he led, amongst other things, its famed Building Research Establishment Centre for Fire Safety Engineering. Throughout this time, or his time in America and Europe, he conducted experimental studies for every possible agency, including NASA, on mines, tall buildings, bushfires, urban wildland interface, tunnels, aircraft, spacecraft, etc. And he produced a plethora of publications, and PhD students participated in numerous landmark fire forensic projects. Brownsville Fire, Sago Mine Disaster, Texan City Refinery Explosion, the Space Shuttle hangars in Florida, the Heron Tower in London, the Bolano Supermarket in Asunción in Paraguay, and the collapse of the World Trade Center. Now, perhaps it is the degree of initiative that is shown in taking advantage of dormant opportunities that made his profile very public in recent years. In 2006, for example, he set a condemned 24-story high tower in Glasgow alight in an attempt to understand how blazes affect buildings and in the attempt to shed light on why the Twin Towers collapsed on September 11, 2001. His experiment was eventually made into a documentary for the BBC Horizon programme. Now, the portrait image that you see behind me shows him almost as a post-apocalyptic Mel Gibson, Mad Max-like adventurer on the foreground of what it may look like Melbourne University's car park, where part of the original Mad Max, in fact, was actually filmed. In fact, the picture was taken in 2012 at the Rolex Center at the École Polytechnique Fédérale in Lausanne, where he was appointed to the prestigious annual chair in Innovation for a Sustainable Future that the foundation of the Swiss merchant bank Landau sponsors in the School of Architecture, Civil and Environmental Engineering. And the chair is a blue sky position offered to people who, through that work, have shown that they have significant contributions to make to the integration of the debate on industrial and environmental change between disciplines. And indeed, José Torero interests are broader than the fire safety of complex environments. They include sanitation, waste management, and contaminated land remediation, and thus betray an inclusive approach to designing our world, an interest in enacting and preempting rather than simply reacting. As a winner of several prizes for the communication of science, he's shown here imparting his ideas on human composting and working his magic on an interested computer entrepreneur that just so happened to sponsor a new toilet challenge with the Dutch Crown Prince shown in the background. In 2012, Professor Torero joined the University of Queensland as the new head of the School of Civil Engineering. And from what I understand, is adjusting to Brisbane climate very easily, and is possibly a climate which is of comfort to his now even more hectic professional schedule from down under. He continues in his numerous international editorial, chairing and board duties in the field, but he's also taken up his research in and on Australia, recently by joining forces with architects to study the possibilities of designing tall timber buildings. I don't have images from his proposals for additions to the University of Queensland campus, but it is only a few days ago that the Office of Skidmore, Owings and Merrill released the Timber Tire Research Project in Chicago that sees the participation of José Torero and the University of Queensland. And we hope that, even through events like this, we will be able to steer his focus and time back on us, to explore how the proper understanding of the behaviour of the elements that we have been fighting for centuries can be used to sustain and enrich the future spaces of our lives. So let's tonight lecture How Do Buildings Burn? Be the stepping stone for this new adventure. José Torero.
Thank you very much for the very kind introduction and for the invitation to give this address. I think it's truly a pleasure to be here. And I guess I have never been referred before as Mad Max, but I welcome the reference and thank you very much. And I'm a little bit humbled by the introduction and also by the fact that we discuss fire as something that is so important in the way in which we put our built environment together, and you know, for what it is, aircrafts and trains and all these things. I mean, the truth of the matter is that when you really think about it, actually, fire is something that, while present in our everyday life, it is something that fundamentally, as individuals, we really don't see necessarily as a great risk. Many people will actually even believe that the fire safety problem is a problem that has already been solved. And by means of regulation and some measures that we put in place, the problem really is truly non-existent. I think I will dare to be able to say that if I was to ask the question to all of you, if you actually feel safe in this room, most likely the answer will be yes. And in general, when you move around tall buildings or you move around different spaces, shopping centers or your homes, you will never feel necessarily this perception that you are at risk. And therefore, because of that, as a society, we have a tendency not to be proactive at trying to address the problem of fire in a way such that we encourage, for example, our cities and our governments to continue to invest and support the development of our understanding of fire safety in the built environment. So in principle, there is a little bit of a duality in this discussion that is quite interesting to analyze, because on the one hand, every time that there is a fire, we see it on the television, and these images, bushfires, home fires, shopping center fires, these images tend to be quite vivid and generally do bring a little bit of fear to us. But at the same time, in an everyday life, we seem to believe that we're perfectly safe, and we don't have this urge to demand improvements. And so the field of fire safety as a research field is a field that constantly struggles between these two opposites. One is the fear, and the other one is discomfort, in which we believe that this discipline has taken care of the problem. Needless to say, if you look at the statistics, and you compare fire losses, both in life and property losses, with most other disasters, you will find out that actually fire is truly a negligible problem. We rarely lose people in fires, and so you compare it to, for example, any kind of major disease, or you compare it to car accidents, even to floods or typhoons, most likely, life loss in fire tends to be quite negligible. Now, in a similar manner, when you're looking at property losses, I can even dare to say that insurance companies, for example, make a killing on fire safety, because it's such a rare event that fundamentally there's enough fear on people that you continue paying your insurance, but the bottom line is that it happens so rarely that they rarely have to pay back. When you compare it, for example, with an earthquake or a flood, where the losses are immense, then fire safety doesn't seem to be really a major loss. So we operate in this environment, and to that we have to add the fact that we all seem to be, in general, experts in fire. I have found myself a million times where I try to explain to somebody something about fire, and instead of me trying to explain it, I get lectured. And I get told, this is the way it works. And it happens at a professional level, it happens at a personal level. You could imagine, my partner yells at me all the time about things that are associated with fire. I keep telling her, you're going to burn down the house, and you know nothing about this. And the truth of the matter is that it's a little bit like football. You're sitting in front of the television, and everybody is more knowledgeable than the player and the coach, and everybody's screaming what the player should be doing. And I think in fire it's a little bit the same. And you can add to that level of complexity the fact that we have a very poor definition of competence, because when you think of who the competent authority is, or who is competent in fire safety, the first thing that you think is the fire service. And the fire service is the first thing that comes to mind. And while I truly will by no means tend to imply that the fire service is not competent when it comes to fire, they're two very different disciplines. I can guarantee you that if I was to decide to walk into a fire and grab the hose and try to extinguish the fire, I would be put in jail, because I will never be considered to be a competent person when it comes to firefighting. Nevertheless, when it comes to fire engineering and looking into how buildings burn, there is a tendency to believe that the fire service, for example, is the competent authority, when in reality their training and education in areas of engineering, in areas of building infrastructure and all these things, is not necessarily the same as the one that you will have when you are involved in an engineering discipline. So these are very different disciplines, and needless to say, they could converge. You could have an engineering office in the fire service and educate the fire service to be engineers, but they're not necessarily convergent areas. So the point that I'm trying to make is that we live in this environment where we believe that this is more or less a solved problem. It's nothing that we feel is imminent, that we really need to resolve. So we have a tendency to believe that there's nothing to be done. And the point that I will try to make in this presentation is that this is not a fact that we have to basically rely on and basically accept that the problem is solved. This is an evolving problem. What happens with the built environment is that the built environment constantly changes. That basically the industry is always innovating, bringing new products, buildings are getting taller, spaces are getting larger, you're making longer spans, you're using timber for very large trusses, you're doing all these different things that are constantly changing. And with the imagination of the architects, with the knowledge base of engineers, we are transforming the built environment on a constant way. And that occasionally catches up with us. And this problem that we really think that we have integrally solved, all of a sudden comes to bite us. And this is a concept that I think is a very unfortunate concept, because fire safety has been traditionally a reactive discipline. One in which we react to the disaster and then all of a sudden we revisit everything that we do. We design by disaster. And the moment we design by disaster, all of a sudden we are sparing people's lives, fundamentally because we have not a capacity to understand that as the built environment evolves, our practices in fire safety need to evolve with the built environment, and we cannot wait until the disaster hit us before we actually start working to try to improve our practices and the way we're doing. So we cannot forget the fact that we need to understand how buildings burn. If we don't understand how buildings burn, we're always going to be waiting for the disaster to happen. So then we revisit what we do, and all of a sudden we begin to understand what we have done. And so I'll try to basically emphasize the idea of proactiveness and the idea of trying to understand what we're doing as a proactive way of addressing a problem that is constantly evolving. It's not a problem that has been solved, it's a problem that might be in a good stage right now, but as things change, the problem is going to come back. So the question is, basically how do buildings burn, and where did we come from, where are we going, and what should we be learning about this? So these are the kinds of things that we are familiar with. So bushfires are something that is very common in this part of the world, and it is one of the big challenges that we are addressing. It is not the fire that is within the building, but it's the fire that comes from the outside and attacks the building. Now, in principle, what tends to happen is that you have this environment that eventually can go into fire, and this environment is going to affect the way the buildings in that environment behave. Now, if the building is properly designed, and the building is properly maintained, and the building has everything that it needs, then fundamentally the event will be an event that has no impact on the infrastructure. Now you're going to say, well, that's impossible. A forest fire is extremely complex, and it has an enormous amount of heat and unmanageable event. Obviously there's going to be an impact. Well, the truth of the matter is that you're probably right, but you're not right because of fundamental reasons, but you're right because of the way in which we design our built environment. If I was to make a point about how to create absolute fire safety, I could make that point very easily. I would say, well, you all get out of this room. I will make this room designed out of stainless steel. I will make sure that every bench is made out of metal, and I will force every single one of you to shave your heads and take all your clothes off before you enter the room. All of a sudden, I have no fire safety problem. Okay? So the bottom line is that I can fix the problem. Okay? The problem is our society willing to fix it with such drastic measures? And the bottom line is no. We want to live in a very nice house. We want to make that house out of timber. We want to have very large windows. We want to do all these things. And we happen to want to place it in the urban-wildland interface. Okay? So we put the house in there, and then we sit down and ask ourselves, why did my house burn when I had a bushfire? This is a man-made problem that we have created. Now, can we fix it? Of course we can, but are we willing to fix it? That's a different story. Okay? So one of the problems that we face is our building facing the fire. Is the building that actually has to deal with the fire, and what do we have to do to make sure that we address the problem in a way such that the risk that we are taking is actually one that we're willing to accept. The problem is that many times we might be in principle willing to accept because we are comfortable. And we say, well, that's fine, I have my building and all that is very fine. But then when the fire hits us, we realize, maybe this was not such a great idea. Once again, the reactive problem. Now, the other opposite scenario is when we have a building within a fire. So this is a fantastic building. So this is the CCTV tower in Beijing, designed by a famous architect called Rem Koolhaas. And basically, the idea of this tower is that it's intended to be a dragon. So this is the head of the dragon, and this is the tail of the dragon. Unfortunately, in this particular case, the flames came out of the tail and not from the head. And I mean, you're laughing, but this is a major fire. Now, this is where the problem is. Now, if I have a fire in a building, is this the intended consequence of the fire? The problem is not that I had a fire inside a building. I can tell you perfectly clearly that the probability of having a fire in a building is 1. It is going to happen. It might not happen today, it might happen next week, or it might happen in a few years, but somebody is going to do something that at some point is going to create a fire. In 99.99999% of the times, the building will respond appropriately. And all of a sudden, what your fire was disappears. It's contained. It doesn't have major consequences, and it does not make the television. Okay? But there is the occasional case, like in 2009, where a simple firework hits a zinc cladding in this particular building, and fundamentally the entire facade of the building goes on flames in less than 5 minutes. Okay? Fortunately, this building was empty because it had just been finished, and it was to be opened, a few weeks later, and therefore there was nobody in the building. But this building has a massive atrium in the middle, so if the building would have been fully occupied, we would have been talking about thousands of people dying within that building. So in this particular case, we can say we were lucky that there was nobody in the building, but on the other hand, here you have what was intended to be an architectural gem, until 2013 remained completely burned down. The cost of repairing that building is astronomical, and now they've taken over the building and they're basically repairing it, and it's pretty close to completion right now. But it took fundamentally almost 5 years to make the decision of actually rebuild this building because of the cost, despite the fact that it's a landmark building in the center of Beijing. So in a way, this is the unintended consequence. This is a part of the problem that we never expect we were going to see. When we designed that building, the fire problem was resolved. And if we actually had a fire, that fire should have remained contained, and it should have never made it to the newspapers. Okay? So this is what we do when we understand how a building burns. So we put a fire safety strategy that is intended to control the fire. If we don't do anything, this will be the outcome. Or if we do it wrong, this will be the outcome. So if you look at history and you try to define what a fire safety strategy is, historically we've always done the same thing. You look at this particular building here, this is a Taipei 101, and this used to be for a long time the tallest building in the world. And if you think about it, what do we do to try to prevent the consequences of fire? We accept, first of all, the fact that there will be a fire. Once we accept that there will be a fire, we do everything to try to manage that fire in a way such that the consequences are the minimum possible. So we put together what we call a fire safety strategy. Now, the fire safety strategy focuses on a number of very, very simple things. The first one, and most important, you are protecting the lives of people. So you have to make sure that you have an appropriate strategy to make sure that people can evacuate the building in a way such that they are not hurt by the fire. Now, what does that entitle? Very simple. You have to put a detection system, and every one of these buildings you will find the smoke detectors and all these things that eventually give you an alarm. And that alarm is the onset of the evacuation. People start moving. You signal correctly so that people can get out of the building, and once they get an alarm, they start moving. Now, people are going to displace themselves away from the fire, so if your fire is here, people are going to move away from the fire. In a very tall and complex building like this, you cannot get everybody out because you don't have the stairwell capacity to take everybody out. So what you will do is displace people away from the fire, and this is what is called staged evacuation, which is basically some people will wait while other people start moving out, and you privilege the access of the fire service to try to control the fire. So this is what we call crowd management. So we put a system by which we are managing the crowd in a way such that we can guarantee that people behave in a rational manner. We try to move them away from conditions of panic by putting them in a safe environment where they still feel that they can stay without really entering into a situation where they become stressed. So we have mechanisms of crowd management that could imply people that are basically moving people around and so forth. proper design, egress paths, stairways, and all these other things. So fundamentally, the first step of everything that associated to a fire safety strategy is the evacuation. Then in a complex building like this, you have the concept of compartmentalization. What does compartmentalization mean? That if I'm going to have people waiting here and people taking a long time to move here, I have to design the structure in a way such that I can box the fire. So the fire is not going to spread upwards, it's not going to spread downwards, it's going to get stuck in this particular area, and it's not going to move until all the fuel burns down. Okay? So basically, you slow the fire growth to a point where these people are going to be safe and these people are going to be safe, and you minimize or eliminate any kind of smoke spread. What really kills people in most of these complex buildings is not the heat, but it's the inhalation of toxic smoke. So you want to make sure that the smoke is compartmentalized and nobody actually is receiving the smoke originating from the fire. So in principle, you're moving people out, and as you're moving people out, you're trying to box the fire in as effective manner as possible. In a tall building, vertical compartmentalization is absolutely critical. If a fire starts spreading upwards or downwards, like in the building that I showed you before, in the Remco House building, fundamentally you're endangering the people up here and the people below. So you have to make sure that the fire gets boxed in this particular area, and compartmentalization is particularly important. So then you have the response. And we put several mechanisms or several layers of response. You can have automatic response, and that's what we call the sprinklers. So we have sprinklers or water mist systems or whatever, which are systems that basically attack the fire in an automatic way. You know, people have seen in films that, you know, James Bond comes in and with a lighter, he basically activates a sprinkler and water falls all over the place. That's ridiculous. Okay, that doesn't happen. If you open a sprinkler, water will come where the fire is. And that's the only sprinkler head that will open. But fundamentally, you have a mechanism by which you have an automatic system that attacks the fire. So we use that as a mechanism of response that is the redundancy. The primary means of protection is to make sure that people can move safely and that I box the fire. And my redundancy is attacking. Why it has to be the redundancy? Because sprinklers are not infallible. So I cannot argue the fact that if the sprinklers fail, then everybody dies. So the primary means of protection are this, and this is the secondary means of protection, or the redundancy. All safety systems need to have redundancy. The next form of redundancy is the fire service. In the case of a tall building, they have to come in from an external way. But if the fire service has to intervene, there you already have a major failure. All of a sudden, you've moved beyond the capacity of the building to respond to the fire, and you're getting into a position where you need help from the outside. But the fire service is the last line of redundancy. Now, in a tall building, as I say, it's external, but it could also be internal. So the in a tall building, it's internal, and in a short building, it will be external. This will be the ladder, so you can attack the fire from the outside. In fire, generally, we define a tall building as the height of the ladder. So if you can attack the fire from the outside, that basically is a short building. If you cannot attack the fire from the outside and you have to go in, then it is a tall building. Okay? So you can have external and internal attack by the fire service. And finally, your other primary means of protection is structural integrity. There is no point in having all these other things if the building is going to fall down on top of you. Okay? So you have to guarantee some form of fireproofing in such a way that you guarantee the structural integrity. A critical and extremely important thing in the fire strategy is you require adequate maintenance. You're putting all the systems in place, and all the systems in place are dormant, and they're waiting for the fire to happen. So if you don't maintain them correctly, you have a program of maintenance, then all of a sudden these systems, the day you need them, they're not going to work. So the proper design and the maintenance are the things that guarantee that the fire safety strategy is going to work. So at the end, a good strategy leads to an acceptable outcome. And that's the principle by which we solve the problem. The reason why fires don't kill a lot of people is because we have a good strategy properly designed and adequately maintained. Okay? So otherwise, when we had a fire, the fire will always lead to a disaster. Now, the truth is that here you have a perfect example of an adequate strategy. Here you have a fire in a tall building that is perfectly contained to a floor, is perfectly compartmentalized by fire doors, so it doesn't move beyond this particular space here. That's exactly the way it's supposed to work. It's a cheap, old housing building, for low-income families that nevertheless works perfectly well. There you have a very good fire strategy, very robust, working adequately. Okay? A bad strategy would have allowed the fire to propagate upwards and downwards. It would have had smoke coming out from left and right, and basically you would have had all sorts of other issues happening in there that in this particular case are not happening. Okay? So as simple as it looks, this is an adequate fire safety strategy for that particular building. Now, let's go a step back. The origins of fire safety. How does this cycle happen, and how did we evolve in this process? We have all these pictures of the Great Fire of London, of the Great Fire of Chicago, of the Great Fire of this and that. The bottom line is that this was the no strategy solution. In the past, before all these great fires, nobody really understood fire enough to be able to put an appropriate strategy, so we found ourselves with these massive conflagrations. And history has a whole list of them that start from the 1600s all the way forwards. Only by the end of the 19th century we start realizing what was going on, and we start recognizing that we needed to put a fire strategy in place. And as you see, it's an evolution process. What brings this up? We had all the great fires in the 16th, 17th century that destroyed the medieval cities. Then we went into a period in which we had created these quasi-modern cities where fires didn't become a big problem. And then we landed with the Industrial Revolution that densified cities again, and all of a sudden the cycle starts all over again, and you get this new generation of great fires that happened at the end of the 19th century. Okay? And at that point is when we recognized that we had to put a strategy in place. And basically we created all these new rules that we call codes and standards that fundamentally emerged from the experience of firefighters, from architects and engineers of the time that didn't really understand fire. Fire is a combustion process that deals with fluid mechanics, with heat transfer and all these things. None of these things were understood at all at the time. So it was experience-based codes that were created, and they put the cities in place in a way such that they dealt to a better outcome. But the truth of the matter is, was a very, very, very poor understanding of all these processes that we call nowadays fire dynamics or structural behavior or human behavior that we really didn't understand. It was just an intuitive thing. And we came up with a big list of rules. Okay, those rules, for example, created separation distances. So we were forced to separate buildings from each other, creating big gaps that prevented the fire from spreading to one building to another. Where we actually could not separate the buildings, we create compartmentalization. So we created these walls that did not enable a fire to go from one building to the other. We created size and separation of windows that that prevented the flames from going from one window to the other. And we created maximum egress distance that guaranteed that people could actually get out of the building before the fire reached conditions that were intolerable for individuals. And the list goes on and on and on and on. We put a whole series of rules, including the professional fire service that actually started in Edinburgh by this gentleman called James Brable, which is the first professional fire master. So basically we created all these things intuitively with very little knowledge to try to enable us to deal with the problem in an appropriate way. And one of the big things that we created, and this is a very, very interesting one, is the concept of fire resistance. If you look at this picture, this is a very interesting picture because you have a very nice fire resistant beam and very poorly performing non-fire resistant beams. This is timber and this is steel. Steel had entered the construction industry at the time, and people didn't really understand after the Industrial Revolution how to really use steel appropriately in construction. And there was a whole bunch of disasters that actually resulted in this. So the concept of fire resistance emerged as a result of the obvious weakness of these new novel construction methods. So we created this concept of fire resistance to respond to this new problem that came in with the introduction of steel into the construction system. So what was the concept of fire resistance? Basically this, a little curve. Okay? So this curve here that basically is time in the x-axis and temperature in the y-axis represented what we call the standard temperature time curve. Okay? So what is the standard temperature time curve? It becomes the worst possible fire you could possibly have. So people start burning in a box. As fast as they could, they were throwing wood in there to try to make sure that they got the hottest possible fire they could get. So they repeated the test a number of different times to try to achieve the worst possible fire scenario. So basically they run the test hundreds of times until they finally created a whole set of curves that fundamentally they drew an envelope to it. Now the fire could not be worse than this. This is the hottest possible fire that you could get. It was the envelope to every single test that they had done at the time. Now the fires, as you put the fuel in, they heat up, they burn all the fuel, and then eventually they die. Okay? So basically what they did next, they defined what they call the fire rating. And what is the fire rating? Is the time that the building has to withstand. How did they define that? They define it on the basis of how long would it take for the fire to burn out. If I have 60 kilograms of fuel, how long would it take to burn out? How many kilograms does an office have? 60 kilograms per meter square. So if that takes 30 minutes to burn out, then I will say the required fire rating for an office is 30 minutes. Okay? So what am I guaranteeing? That I get the worst possible fire for the longest period of time. So if instead of having an office, I have some sort of factory, where instead of having 60 kilograms, I have 120 kilograms, so then it takes me 60 minutes to burn. So I define a fire rating of requirement of 60 minutes. If I have more fuel, then I put 90 or 120 and so forth. So as I increase the fuel load, I increase the rating. Okay? So if you think about it, what I have created the worst possible fire for the longest period of time. Can it be any worse? It can't. It cannot be longer because I've already burnt out all the fuel, and it cannot be hotter because this is the envelope to all that. So then what happens if I test my structural systems and they don't fail under these conditions? Can they possibly fail in a real fire? They can't, because the fire cannot be hotter and it cannot last longer. So if they don't fail in the test, they will never fail in a real fire. So what we did is we created all sorts of rules. We boxed the fire in such a way that everything around the fire is much stronger than what's happening here in the fire. So basically means that if this piece fails and the loads get redistributed, then all of a sudden nothing happens because the failure cannot propagate. So I box the fire by creating compartmentalization, and I put the worst possible fire. So all of a sudden, if I take the test and basically I reproduce in a furnace that curve, and I test my structural element, and I find some failure criteria, what is the temperature at which the material fails, then I can test the structural element and define with that failure criteria what is its fire resistance. So this beam that I put in here lasts 50 minutes. I take a safety factor and I say it has a fire resistance rating of 30 minutes. If I require 30, then I'm fine. If I require 60, then I insulate it, put fireproofing to try to make it 60, until this curve goes down enough that it gives me the rating that I want. Okay? Now, but the concept of all this, despite all the details, is the fundamental fact that I have a very large safety factor. Why? Because I have the worst possible fire for the longest period of time, and I'm testing my structural elements in a way such that they meet that requirement. So why do I need that big safety factor? Because I don't understand anything. In 1906, when we developed the fire resistance curve, we didn't understand how structures behave. So I put the worst possible case. Okay? So basically our poor understanding enabled us to do that. We didn't understand any of these things. So basically we put the worst possible scenario as a huge safety factor. So the fire resistance, got embedded into codes and standards in 1906, and basically has lasted until today, and it was society's responsibility to guarantee safety. Huge safety factors? Yes. Can we live with them? Yes. Why? Because we don't know the details. So we have to live with those huge safety factors. So at the end, this was the result. I could guarantee to the structural engineer that no matter what he did, that building was not going to collapse in a fire. All of a sudden, I can build tall buildings. Why? Because people can be in the building for as long as I can, so long I protect them from the smoke, so long I protect them from the heat, and so long I'm moving them slowly out in an effective way, the structure will never fail. So height disappeared from the equation because the building will never fail. It will withstand burnout. The fuel will burn completely and the structure will remain in place. All of a sudden, you could do tall buildings. So this breakthrough in regulation enabled the construction of all these tall buildings. So the real gain was that I had better informed codes and standards. I created a rule that enabled me to prevent failure at all costs. And all of a sudden, I gave the structural engineers the freedom to build extraordinary buildings. And the result is that structural engineers transform cities. So this little piece of knowledge of fire resistance opened the door to the use of steel and concrete and all these new materials into building all these tall buildings. So that's when we are ahead of time. We were ahead. We created the knowledge. We opened all the doors. And we created all these buildings that were fundamentally safe from a structural perspective. This gentleman here is called Howard Emmons. So Howard Emmons was a professor of applied mathematics in Harvard University, and basically he got into fire research during Second World War. Do you have any idea why he got into fire research during Second World War? The same thing happened in Britain with Philip Thomas, in Japan with Kunio Kawagoe, all these people that we consider the parents or the fathers of fire safety. You know, why did they get into fire safety? Because they wanted to make sure that they could circumvent all these great things we had done before to protect people. Their objective when they got into fire research was to make sure that they make all these structures fail. They recognized that the great way to create morale damage into cities was to let fires propagate and destroy buildings in a very effective way. A bomb can destruct only a very small area, but if it can induce a massive fire that results in huge propagation of the flames and in collapse of the structures, then all of a sudden you are imposing a much more severe damage to the city that the bombs can do. So all these people were working extremely hard at figuring out all the details of fire safety in such a way that they could destroy all the rules that we have put to protect us. But in consequence, what did that gave us after the war? We were so ahead. We understood so much about buildings and how fire behaved in buildings that fundamentally we had a period of great innovation in our understanding of fire and all its consequences. So as I say, there's a whole list of them. You know, Emmons was in Harvard, Hotel in MIT, Kawagoe at the University of Tokyo, Thomas at the Building Research Establishment in the UK, and they were all devoted to try to understand how to destroy things with fire. So fire safety, all that knowledge went into a set of improved codes and standards that put us very much ahead with incredibly nice codes and standards. What happened after? What always happens. Cities start transforming themselves and start changing all over again. And all of a sudden, city density increases, building complexity increases, codes and standards start falling behind. And we hit the 1960s. Every fire that has a name happened in the 1960s. The Joelmas, the Andraus, the Dupont Plaza, every single fire that we've given a name happened in the 1960s. Fundamentally because we introduced plastics into buildings, we eliminated the concept of compartmentalization because we wanted open space, open floor plans, and all these things. And all of a sudden, all these rules that we had put in place start fading out because we forgot how buildings burn. We completely forgot about the processes that actually make buildings burn. And the result is that we got huge problems with smoke management. Smoke in the MGM Grand Fire in Las Vegas, fundamentally it was a problem of smoke transport. Smoke filtered through all these ducts of HVAC and all of a sudden started killing people that were literally 10 stories away from the origin of the fire. You know, we had problems with material selection. We put plastics all over the place. This is a Joelmas building and you had plastic cladding that burned all the way to the top. and all of a sudden we had a fire that had spread beyond the area of origin. We had huge structural problems. We have 2 concrete buildings collapse in Sao Paulo in Brazil, and so forth. But fundamentally, the complexity of what we did with our built environment fundamentally challenged all the knowledge that we had built in the 1940s. And we found ourselves with buildings that were way beyond the complexity that we can manage, and we forgot completely how buildings burned. Our codes that we relied on, that we felt that were very appropriate, were not appropriate anymore. Once again, basically the code compliant became a bad strategy. We were a very rigorous code compliant society that had created a whole bunch of set of rules that had served us well until the 1960s. But in the 1960s, it became a bad strategy. And the result was all these big fires that we had in the 1960s. Of course, what is the answer? Reactiveness. All of a sudden, design by disaster, we had all these major messes. What did we do? We started throwing millions at fire research. Okay? Everybody was working in fire research, new methods, new tests. Of course, we had tests that were designed for timber, and all of a sudden we're burning plastics. Plastics melt. We were not taking that into account. Timber produces certain toxic compounds, plastic produces others, and so forth. So we created all new, basically new methodologies, new models, new calculations, and all of a sudden everything starts changing. And our understanding of fire becomes a lot deeper at every level, human behavior, fire dynamics, everything. So we understand everything much better. And all of a sudden we realize, wow, this is getting very complicated. It's not about just simple rules that anybody can apply. We need engineers to understand this. We now have tools that require the competencies of an engineer. So all of a sudden we start getting higher education programs. At the end of the 1980s, you start seeing universities teaching fire safety in certain places. In Australia, it was Victoria University, University of Western Sydney. In the UK, it was Edinburgh, it was South Bank, it was Ulster. In the US, University of Maryland, WPI, Tokyo University. All sorts of places start popping fire engineering programs because these tools now are not for everybody. All of a sudden, they require people with certain level of competency. Because a big change had happened. Until then, our game was knowledge-informed codes. So what were we doing? We were learning, improving our codes. And the result, we had better rules. But the rules were rules. It's a recipe, like baking a cake. Okay? What happened in the 1980s is that we learned how to calculate. And all of a sudden, we became an engineering discipline. And that engineering discipline now had tools that require engineers to be able to develop them. So, the problem is a transition, because we started designing for implicit performance, which was basically code-based design. If you follow the rules, it's going to work. How well is it going to work? I don't know. How big is my safety factor? I have no clue. All I know is that if I follow the rules, it will work. That's implicit performance. Now, the problem with implicit performance is that it's one size fits all. I classify a building as a hotel, and I design all the hotels with exactly the same rules. Now, think of what that means. It means that you standardize the space. So every architect is going to complain when I tell them that they have to box their egress paths. It looks ugly. It loses functionality. All my means of egress become unused space that is designed only to be used in the event of a fire. We don't like that. It implies compartmentation. So we need to box every room. What about the open floor plan? Oh, that's too complicated. We cannot do that. Box it again. It's constraint after constraint after constraint. We change everything, the geometry. You cannot even design a roof or a ceiling without constraints associated to the smoke detectors, the sprinkler systems, all these different things that start messing the entire fabric of the building. That's not nice. If people complain about these things, architects don't like fire engineers when they tell them they have to do all these things. We standardize response and we stick sprinklers everywhere. These little things are sticking from every ceiling, but what if I want a really nice white ceiling? All of a sudden, you standardize it. You standardize the pacifier proofing, and you want to have an exposed structure. That cannot happen. You have to cover it with fireproofing. Yeah, but it's nice to have the steelwork. Man, sorry, you have to cover it. So the fire service, of course, gets completely standardized, professionalized, and you have all these things going on. But this implies an enormous cost to be able to keep this idle workforce waiting for the fire to happen. So fundamentally, this approach of one size fits all has enormous safety factors. But not only enormous safety factors, but also a loss of function. Who wants to have a stairwell like this in the back of their building? Nobody. But it's an egress path, and I need to have two of them, so I don't have anywhere to put them. Let's put it in the backyard. Okay? And that's what ends up happening. An architect wants to have a feature staircase, little beautiful spiral stair, box it. Because it cannot, it's a vertical shaft, and that puts the smoke in place. It's a mess. Of course, enormous waste. This is foam that is in a hangar when you're trying to fight an aircraft fire. Okay, and enormous safety factors. You know what the safety factor of a sprinkler system is? 10,000. I'm not joking, I'm being serious. You throw 10,000 times more water than the one you need. Why do you do that? Because you have to cover for every possible size of fire that you have. One size fits all. The same sprinkler is going to kill a little fire as it's going to kill a bigger fire. So you have to over-dimension the system to a point that is absolutely unsustainable. The main problem with implicit performance is, despite the fact that you're putting a huge safety factor, you can never spot the mistakes. Why? Because it's implicit performance. You follow the rules. But if somebody did something that might have fallen within the rules, but it was novel, different, whatever, that somehow took us outside the picture, we cannot spot it. So we have these unidentified mistakes all over the place. This is the Windsor Tower fire, perfect example of the failure of a curtain wall. Okay? So what's the problem with all this? Is that it's an unsustainable strategy. We went from no strategy to a code-based bad strategy to an unsustainable strategy, where the waste and the over-dimensioning and the unwanted mistakes are so large that fundamentally we find ourselves in situations like this. This is the World Trade Center, and people will argue anything you want about the World Trade Center, but that was an engineering mistake that we didn't notice. It was a structural failure that was not anticipated by those who designed the building and could not be anticipated because the codes didn't require the level of analysis that would have identified the weaknesses of that structure. Okay? So fundamentally, this is an unsustainable strategy. Now, what's the alternative? The alternative is what has happened in the last decade. So what used to be a very nice strategy of basically blocking and boxing the fire has all been transformed. And fundamentally, we have accepted this idea of performance-based design. What we learned in the 80s and 90s, now we are using as tools for design. We are using engineering tools in a way such that we can have explicit performance of the building. They change from the implied to the explicit. Calculate the performance of the building to establish what is the effective safety factor and what is an appropriate safety factor that doesn't waste and give me the right answer. So the focus on sustainability and not losses is what has changed in the last decade. We want to have the right solution at the right cost, at the right level of waste, with the safety factor that is adequate for the problem. Now, the unfortunate thing, or the fortunate thing, is that to be able to use this kind of tools and to be able to do explicit performance, you're addressing a completely different problem. You're not dealing with the codes and standards and the rules and the recipe. What you're dealing is with a problem that starts with the material, that looks at the way it burns, material flammability, that eventually produces smoke and heat that is going to be transferred through complex turbulent flows and very complex combustion chemistry, that effectively the heat transfer and fluid mechanics are going to heat up the structure. And effectively, you have to understand then the structural behavior in such a way that you know how this building is going to perform. Now, that structural behavior then has to be able to enable people to evacuate in an appropriate way. So you need to understand the physiology, the psychology, the sociology of people that are moving within the building, so you know what time you need to get them through the system in an effective manner. You have to be able to convince the architects to introduce this into their design practices. That's a big challenge, believe me. And the problem is that not only that, but you have to make sure that this is embedded within the education of people, so that the regulatory law and everything that we have that guarantees that this process works actually works. So there's an element of education, there's an element of accreditation, there's an element of understanding all these things that becomes very important. But this is truly the only sustainable way, because it's the only way you can get the proper safety factors and you get the right answer and you understand explicitly what the performance of your system is going to be. So at the end, this is where we are aiming. This is what we're trying to do. But the one thing that we need to try to understand is that this is all also in the context of the way in which we build. So for example, construction detailing is a very practical thing. So it's all very nice to have all this great knowledge and deliver these wonderful buildings, but if we don't construct them correctly and we don't do the detailing the way it's supposed to be, we're going to get it wrong. Here's a perfect example of how things can go wrong. Today, we use curtain walls. A curtain wall is very different to old-fashioned construction in the sense that instead of being attached to the concrete slab here, it is hanging from the concrete slab to give continuity. What is so different about that? If I have something sitting on the concrete slab, it's the concrete slab that protects me. So it separates the floors. And if I design the concrete slab correctly, then I can guarantee that the fire will not move away from one floor to the other. Okay? Well, if I hang this, it is at the connection point where you get the problem. Okay? Because this is the weak link. This is the vulnerable point. The concrete slab is fine, but if this fails, then the flames go in and they spread to the next floor. A curtain wall is completely different to a standard wall on concrete, because it changes the focus from the concrete slab to the connection point. Now, let me show you this detail of a curtain wall of a very tall building in Europe. Okay? I put here in red the gap between the concrete slab at this end and the very lightweight aluminum curtain wall. Okay? The gap basically forces the concrete slab in front of the glass. How can I seal this if the concrete slab is in front of the glass? How can I guarantee that the frames are not going to go through if I have a concrete slab that is facing a piece of glass? That's detailing. That's the fundamental detailing of a building that makes the solution impossible. This is a building that is perfectly compliant with the code, because if I fill this up with fireproofing, all of a sudden it complies. But this detailing is going to guarantee that the system will never meet the intent of the code. The intent of the code was to protect one floor from the other one. But while I have concrete on glass, doesn't matter what I put inside. This glass is never going to be able to withstand the thermal expansion of the concrete. So when the concrete starts expanding because of heat, it's going to break the glass immediately. So those level of details that go together with all the theory are fundamental. So the individuals that actually understand the theory and understand the practice are fundamental to this discipline. So what is the sustainable strategy then? Now the problem is complex. What happens when you have a very, very, very complex problem? What happens when you want to get brain surgery? You have a problem, you have a tumor in your brain, and you want to get brain surgery. Who are you going to call? Your friend? The fire service? The paramedic? The nurse? Who are you going to call? The doctor. Okay? What is the difference between the doctor and everybody else? That's the competent professional, no? If you want to design a fire safety strategy, who is the competent professional? This is a very complex design process and requires a high caliber professional. What defines a high caliber professional? And this is something that most people don't understand. What is the difference between profession, occupation, and trade? The profession is something that regulates the individual. When a doctor becomes a doctor, it's the doctor that you're regulating. It's the individual that you're qualifying. And then it becomes a monopoly. It is only doctors who judge doctors. It is only doctors who accept doctors. It is only doctors who criticize doctors. And nobody can criticize a doctor other than a doctor because they don't know enough. They're not competent enough because it's too complex of a discipline for anybody from the outside to do that. What is a trade? You regulate the activity. Bankers do that. A doctor can be a banker. A mathematician can be a banker. You know, anybody can be a banker so long they do it right. So we regulate the trade. We put all these rules that people have to follow in such a way that the activity is regulated, not the individual. Now, code compliance is a trade because you create codes and standards that regulate the activity. Any individual can come and do a code compliant design. You don't need to regulate the individual, you regulate the trade. So at that point, there's no monopoly. There's no right to monopoly. Very different. And an occupation is an unregulated space where basically market variables are going to decide who is a good art historian. There's no qualifying here. It's not that one is better than the other one. They're completely different in nature, and they're associated to the activity itself. If the activity is so complex that only a professional can do it, then it is a profession. If the activity can be structured in a way such that by following certain rules, you can do it right, then that's a trade. And if the activity doesn't need to be regulated for whatever reasons are, then it is an occupation. So all of a sudden, fire safety moved from being a trade to being a profession, but we never noticed. So we didn't create the educational vehicles, we didn't create the accreditation process, we didn't create anything, we just allow it to happen. And all of a sudden, we find ourselves with an activity that used to be a trade, that today requires a profession, but is operating as an occupation because it's unregulated, because the trade now has allowed performance-based design, so I don't need to follow the rules. Okay? I have no mechanism of accreditation, so anybody can do the work. So fundamentally, you have a profession that used to be a trade that is operating like an occupation. Recipe for disaster. Okay? So all of a sudden, we're talking about regulation. In the case of a profession, is the accreditation. In the case of a trade, it's a code of practice. We eliminated the code of practice, and we never put in place an accreditation. Beyond that, the accreditation is the prerogative of a professional body. But it requires, in the case of engineering, of a two-tier system. One that accredits a university or a degree that enables you to say that you have the capacity to learn how to learn. You're ready to enter the professional world and start learning on your own. Once you enter the professional world and you start learning on your own, then your experience gets accredited by the professional body and you receive your certificate that says you're a professional in the discipline. Well, this one, we have the experience one, but we forgot about the universities. And we never developed a proper degree in fire safety engineering, despite the fact that now we recognized that it was a profession. And in principle, the degree is a necessity. It's a fire safety engineer, and it's a first-tier accredited program. Today, Australia has none. Australia has one of the most liberal regulatory systems in the world, one of the oldest and most liberal regulatory systems in the world that allows pretty much anything. Okay? Nevertheless, Australia has never produced an accredited first-tier university degree. Now, that is a big challenge, and it's something that really needs to be addressed before we actually can achieve a proper sustainable strategy. So, the question is, given how we operate today, can we deliver a sustainable strategy? And I leave that question for you to answer. But the one thing that I can say is that if you want me to answer why do buildings burn? Fundamentally, they burn for two very, very simple reasons. One, because they're poorly designed, and two, because they're poorly maintained. Now the question is, do we actually have the framework to enable us to guarantee that we actually have properly designed buildings and properly maintained buildings, given how fast the construction industry is evolving? As I say, I will leave that to you, because the problem is that if we don't, then at the end, we have a poor fire safety strategy. Thank you very much.